Okay, let's unpack this. You've brought us sources on a proof that is, well, it's just magnificent, a real mathematical detective story. It kicks off with this really modern idea in geometry, then it detours through classical algebra and lands, incredibly, by explaining one of the oldest secrets in number theory, the fundamental structure of the Fibonacci sequence.
It really is a story about unity. We're diving into a proof by Sigler and Herbig that solved a major conjecture stemming from Weilberger's rational trigonometry. And our mission for you is to see how the factorization of these uh, strange-sounding polynomials,
Yeah.
spread and spread polynomials, acts like an algebraic Rosetta Stone.
A Rosetta Stone that unlocks the Fibonacci numbers.
Exactly. It reveals their deep structural core.
That is some journey. We're connecting dots, across centuries. We have Norman Weilberger's modern geometry, the classical heavy lifting from Lucas and Chebyshev polynomials, and then the Fibonacci sequence itself.
And what's so incredible is that the connection isn't forced at all. It's actually surprisingly elegant. But to really get the payoff, we have to start at the beginning. Why would anyone want to, throw out the basics of geometry in the first place?
I was wondering that. I mean, I thought geometry was sines, cosines, and square roots. So why did Weilberger want to make geometry rational?
It's all about computational purity. The main goal of rational trigonometry is to make plane geometry completely free of transcendental expressions and square roots.
Okay, so numbers like pi or the square root of 2.
Right. They're irrational. You can never write them down completely, which means any calculation is always an approximation. And that's computationally expensive. It's slow.
Especially on limited hardware. I get it. Every time you calculate a square root, you're spending time and energy. So if we get rid of traditional lengths and angles, what takes their place?
You replace them with their squared rational versions. So lengths become quadrances. If you have a length A, the quadrant is just A squared.
Simple enough.
And this means the Pythagorean theorem, the bedrock of geometry, becomes a totally rational statement. Q of A plus Q of B equals Q of C. No square roots.
That's a huge computational saving right there. Geometry just became pure arithmetic. But what about angles? What happens to theta?
Angles are replaced by spreads. Let's call it S. In a right triangle, the spread is just the ratio of the quadrants of the opposite side to the quadrants of the hypotenuse.
So b squared over c squared.
Exactly. It's always a rational number between 0 and 1. You've just swapped a transcendental concept, Karen, the angle, for a simple ratio of squares.
Which leads us to the spread polynomials, the s and the x. These are the tools that handle combining multiple spreads, right? Instead of all those old trig addition formulas.
You've got it. The spread polynomials are central to the whole system. They're defined by this property that s and sine squared theta equals sine squared of n theta. It's just an elegant way to manage composing spreads. Instead of complex trig, you just evaluate a polynomial. The geometry problem becomes an algebra problem.
Okay, that makes perfect sense. So the spread polynomial is the engine for the geometry. But to actually prove how it factors, the researchers needed what? An algebraic shortcut?
They did. They shifted from the spread polynomial, Sn of x, to a really closely related one called the z-pred polynomial, Zn of x. It's defined as 4 times Sn of x over 4. It's just a scaled version, really, but it's much easier to work with algebraically.
And this is where the real genius comes in. The proof by Sigler and Herbig connects this new z-pred polynomial to a completely different, much older family of functions.
That's the masterstroke. They found this one powerful identity linking Zn of x to the well-known Lucas polynomials. The identity is Zn of x equals 2 minus ln of 2 minus x.
Wait, okay, let me just absorb the power of that. That one little equation completely transforms the problem. It takes this brand new sort of niche geometric polynomial and shows it's just a translation of a classical algebra problem that's been studied for over a century.
Precisely. We don't have to invent anything new. We just have to realize we're standing on existing infrastructure. The Lucas polynomials have this simple recursive definition. They're related to Chebyshev polynomials. Their properties are deeply, deeply understood.
Which brings us to the big mystery they were trying to solve. The Go-Weilberger conjecture. The idea that these new polynomials must have some kind of highly structured factorization.
That was the hunch. Shuxiang Go, who was Weilberger's student, he conjectured that Zn of x factors in this beautiful regular way over its divisors. Specifically that the degree of each factor is determined by Euler's totient function, phi of d.
Euler's totient function. Okay, for anyone listening who's a bit rusty on their number theory, what does that signal?
It signals a predictable, almost perfect structure. It means the factors behave just like cyclotomic polynomials, which are, the absolute fundamental building blocks for roots of unity in number theory.
So the question wasn't if they factor, but if they factored with this perfect clockwork regularity that we see in classical number theory.
Yes. And that's where the proof mechanism is just so clever. Sigler and Herbig didn't try to factor Zn of x from scratch.
No, they used that bridge. They used a known result, the factorization of ln of x minus 2.
That is the key. They knew the roots of ln of x minus 2. They're very specific numbers related to the cosine function. More importantly, the full factorization of that polynomial was already solved. The entire algebraic blueprint was already documented.
So the novelty wasn't cracking the factorization itself.
Yeah,
It was proving that the new geometric polynomial was just the old number theory problem in disguise.
That's it. They just applied that bridge equation.
Yeah.
Zn of x equals 2 minus ln of 2 minus x. You make a simple substitution, y equals 2 minus x, into the known factorization, and boom. The Go-Weilberger conjecture is proven. Instantly.
That has to be one of the most satisfying moments in a proof. To realize you've already solved the problem, you just didn't know it yet.
It really is. It shows how connected this all is.
So once the structure is proven, we can look at the building blocks themselves, these factors called phin of x.
Right, these are the core factors, and this is where the geometry comes looping back in. The sources show that phin of x is the minimal polynomial of the value 4 times sine squared of pi over n.
So the fundamental algebraic factors are rooted in a geometric value. It's literally 4 times the spread for a certain arrangement of lines. The algebra is reflecting the geometry it came from.
It's a perfect closed loop. The geometry needs algebra, and the algebra's factors are fundamentally geometric. Now, hold on to that idea of this perfect algebraic structure, because that is what leads us to the giant pivot, the totally unexpected connection to the Fibonacci sequence.
This part is just wild. We invent a whole new geometry to get rid of square roots, and in doing so, we accidentally explain the math behind, multiplying rabbits?
Something like that. See, the Fibonacci numbers, Fn, form what's known as a divisibility sequence, and that means they can be uniquely factored into what are called their primitive parts. That structure, that factorization rule, looks mathematically identical to the structure we just proved for Zn of x.
The blueprint is the same, but how do you actually get from a polynomial to an integer sequence?
With one single beautiful equation, the Rosetta Stone, as I call it. If you evaluate the spread polynomial at one very special number, x equals 5, you get this identity. Zn of 5 equals -1 to the m minus 1 times 5 times fn squared.
Wow. Okay, so plugging the number 5 into this geometric polynomial spits out the square of the nth Fibonacci number.
Essentially, yes. And because the algebraic factorization of Zn of x has to hold true when you plug in 5, this identity proves the structural rule for the Fibonacci numbers. It proves that f is the product of its primitive parts over all its divisors. The geometry proves the number theory.
And now we have a totally new way to calculate those primitive parts, the PNs. We can use the algebra.
Exactly. The primitive parts are just the result of evaluating those core algebraic factors. Phin of x at x equals 5. It's just Pn equals the absolute value of phin of 5.
Let's do a couple of examples because this really makes it click. Let's take f6, which is 8.
Okay, the divisors of 6 are 1, 2, 3, and 6. You calculate the primitive parts, you get P1 is 1, P2 is 1, P3 is 2, and P6 is 4. You multiply them. 1 times 1 times 2 times 4, it's 8. Perfect.
And f9, which is 34.
The divisors are 1, 3, and 9. The primitive parts are 1, 2, and 17. So 1 times 2 times 17, 34.
Last one, f10 is 55.
Divisors are 1, 2, 5, 10. Primitive parts are 1, 1, 5, and 11. 1 times 5 times 11 is 55. It just works every single time. This structural lockstep between abstract geometry and a fundamental integer sequence is just, it's stunning.
Here's where it gets really interesting. Beyond the pure mathematical beauty, what's the actual payoff here? For someone in engineering or computer science, if you're a developer, why should you care that Zn of x factors so nicely?
It all goes back to the beginning, to computational efficiency. If you were writing code for embedded systems, for low-power microcontrollers, real-time graphics, any system where every processing cycle counts,
then calculating a sine or a cosine, or especially a square root, is a real cost. It burns power and time.
a huge cost. But if your system, say a drone navigating in space, can rely only on rational algebra on quadrances and spreads.
You get much faster geometric calculations with perfect rational precision.
Exactly. And the proof confirms that these polynomial structures are predictable and can be effectively calculated. That points directly to algorithmic improvements for any system that relies on approximating signals.
And the tools themselves are not new to engineers, right? The sources highlight the link to digital signal processing.
Oh, absolutely. The proofs use generating functions, which are, first cousins to the Z transforms that are everywhere in DST. On top of that, the spread, Z-spread, and Lucas polynomials are all part of the same family as the Chebyshev polynomials.
And Chebyshev polynomials are foundational for things like electronic filter design. They're used because they're the absolute best way to minimize error when you approximate a function.
Correct. So this discovery isn't just some curiosity. It reinforces that the very tools engineers already use for efficiency and precision are deeply structurally connected to the most basic components of geometry and number theory. It shows how unified the whole mathematical universe really is.
So, to recap this whole journey, we start with a modern computational question in geometry that leads us to an algebraic bridge using classical Lucas polynomials. And proving the structure of that bridge unexpectedly reveals the hidden mechanism that perfectly factors the ancient Fibonacci sequence.
So what does this all mean? Well, it's a powerful reminder that mathematics is one unified field. An insight from one corner can totally light up another. And it leaves you with this question. If Fibonacci numbers can be so perfectly explained by the structure of a geometric polynomial, what other fundamental sequences out there, the primes, the Catalan numbers, might have their secrets revealed by similar polynomial factorizations? Maybe one last thought for you to mull over. What is the geometric meaning of that number 5? The one number you plug in that unlocks the whole thing. It turns out 5 is deeply connected to the golden ratio, which suggests the entire structure of the golden ratio is somehow fundamentally baked into the very geometry of spreads.